software for open networking in cloud, SONiC. Great contribution from Microsoft in the world of networking. But I have to say they didn't get something quite right. It's the name, in cloud. And think outside of cloud. That's the use case for our talk today. He's Vince from Dell, network architect, and me, Alankar, data center architect from Comcast. What we are going to talk today, a quick overview. So we will look at overview of Comcast data centers, what's in there, how they look like, why we were even looking for a new operating system, details about SONiC, and where we are deploying it at Comcast, and how we are operationalizing it. OK, so the data center footprint at Comcast, we have 8 national data centers, 14 regional, 54 local, a bunch of others, total about like 90 sites. The focus today is primarily on the nationals, because that's where we are doing SONiC. In terms of devices, we are looking at about 9,500 network devices just for routing, switching, kind of. The devices, the count that we know about, which gives us close to 300,000 server ports. And we do 600 plus network changes a month. Again, the changes that we know about. But the complexity where it comes from is the rainbow data centers we build with multi-vendor and all different kind of hardwares and different vendors there. So we have more than 8 vendors for, again, not including any server hardware, which brings 117 different hardware models and 184 different operating systems. Management tools, we don't want to talk about it. Everything is there. So what runs on that hardware? Different cloud platforms, OpenStack Cloud, the VMware Cloud, Kubernetes, Container as Service, Cloud Foundry, and video systems, voice systems, bare metal, all different kind of applications and different kind of protocols. And on top of that, we need to secure that. So there's some segmentation going on in the network, which makes it very hard to operationalize things. And the scale is still manageable. The difference we have from the big web scalers is instead of doing one thing 100,000 times, we do like 100 things 10,000 times. So why we need new operating system after having all those different variations? And that comes to like, OK, what if the whole world spoke one language? The travel would have been much easier. They will all understand the same thing. Yeah, they could have different cultures and different traditions, but I can communicate to them in one language. So the biggest challenge is the automation. If I have these different operating systems and these different hardwares, I need something as a translator to give the same command to all of them. And traditionally, we have been building translation layer on top of the traditional OSs. Like, attempts were made with tailf, and we did use tailf. OpenConfig is another great one. But we still need something more that we can talk the same language. Normalize the hardware variations. So I want all different kind of hardware versions, but they all need to be on same level ground and behave the same way. The software interop issues is a big one. To give an example, I had problem having 2 platforms from same vendor and could not speak ISIS between them because they are using different packet formats. Several days wasted, and the troubleshooting cases, we figure out they are using different kind of hello packets, and one needed padding. So if the operating system is the same, chances are we won't have these issues anymore, and we could save some time in the interop testing and certification internally. Obviously, every time you do something new, we need to reduce the cost, and I want something that is cheaper, and I mean, software has a cost to support. Another big one is break free. With the vendor operating systems, I have a feature built by one vendor but not by other, and now I'm stuck, I cannot use it. Because it has to make business sense for them. It has to lie on their priority list, which is not always the case. We need multi-vendor, we need chip diversity, and we want to decouple not only the hardware software, but also different software components. So if I want, I can yank this stack and replace it, or I can upgrade one at a time, not having the traditional monolithic codes. And out of all that wish list, I still want the luxury to be able to have a phone call and have some support on it. So where that takes us is that's served by SONiC. What is SONiC? Vince?
So raise of hand, before this talk, how many people have heard of SONiC? All right, that's a fifth. And of those people, how many have actually installed, played with it, tested it out? All right, a significantly less amount of people. I only saw about 5 hands up. So underlying underneath the covers, right, SONiC is built upon Linux. And with that, you're able to leverage advanced management tools such that the server guys that are already used to with a common CI/CD, Ansible, Jenkins, Jeff, Puppet, from the management system. So that in itself, as Alankar had mentioned, being able to leverage that for the network. And if we look at the two things there, the ODM and ASIC vendor diversity, as well as the search abstraction layer, that means what we can do is leverage manufacturers such as Broadcom, Mellanox, Barefoot, and it's hardware independent, right? So what we were talking about was being able to use the same software, all the same automation tools to manage the network infrastructure, but the hardware itself can change. We were talking about containers, right? Everything right now, that's what they're built on. And if we look at how this is built, for example, BGP, we can take that stack there, and as the operator, you have the option, you have the choice of being able to pick Quagga, FRR, GoBGP, Arista's BGP, or Juniper CRPD. And again, customize the operating system based upon your specific use case. Maybe you don't like one stack versus the other. Easy to swap out without changing the underlying operating system. What I'd like to show here, and I'm not going to go through all of it, right, is, again, in the user space, you see all the different pieces that are containerized and the ability to maybe pull them out, create your own, and then interact. At the bottom level, we have the actual physical hardware, right? We're talking about the specific ASICs, and then the kernel space where you have all the different drivers, right? The switch abstraction interface sits there to be able to leverage different vendors. And what I do want to highlight here is in a pub sub model. So again, being able to create your own pieces custom to your environment. With this, I'm not going to go through it, but you'll have the slides. I'd like to ask, when was the last time you actually saw a packet walkthrough from a vendor showing getting an update and then programming the fib, right? That's not usually publicly available. A little bit about the maturity of SONiC. 3 releases a year. There's about hundreds of commits a month. We've got about 850 community members. And I actually just checked this morning, there's about 89 supported platforms. So by the time that we had submitted this until today, it's increased in the number of size. Major customers that are actually running this in production, Alibaba, Tencent, LinkedIn, Dell, Broadcom, and Mellanox as far as contributors to the SONiC repository. And then there also is commercial support available for people that want to run open source but still need some form of support. So the advantages of SONiC. Again, designer network operating system. We saw in the slide or two ago, you can change out the routing stack depending upon your specific use case. That next point there, SONiC, it's open source, so being able to leverage that with current vendors as opposed to people with large spend, where they're being able to actually negotiate rates with their current vendors. Because it is a modern operating system, we don't have to worry about monolithic code and all the baggage that comes associated with that. At some point, if there is looking at SONiC, what we mean by here is building the same layer 2, layer 3 stack. You see all the other vendors, everyone, they're building the same feature. If we were able to consolidate on the same person creating that feature, interoperability and stability would probably go up, in my opinion. Zero downtime, being able to upgrade the containers on the fly, and then Alencar will also go through a brief demo of the fast reboot and warm reboot. And part of the CI/CD practice is that's not just for cloud anymore. Everyone has the ability to do this.
Okay, so where are we deploying SONiC at Comcast? We're taking a phased approach, starting from the DC core that we have in more detail in the following slides. How the team looks like, so 5 engineers, and that includes our new boss as well, plus 24/7 operations team. We do have plans to extend it in lower layers and enable more features later. But what's deployed now is pretty simple. We are doing LLDP, BGP, ECMP, DHCP, LLDP, the generic management features, ACL, NTP, TechX, and stuff. We do want to get to some of the layer 2 things next year, including VXLAN and BGP EVPN. So high level, how the Comcast data centers look like. We follow quad design, which means the national DC is divided in quad 1, 2, 3, 4 typically. If you see on the bottom here, there are racks with top of rack switches connecting into spines, further aggregated into ag spine. Going north of it, super ag, and multiple 100 gigs connected to backbone. It's all layer 3 eBGP between the layers. Now, in the center where it says DC core, we're going to zoom into it a little more on the next one, and that's the area where we are doing SONiC. So the DC core is kind of a contained unit. It's like a block that we can repeat in different quads. Each unit looks like 48 switches, 32 spines, and 16 tier 2 spines. They're all same kind of switch, same SKU, Tomahawk 3 based 32 by 400 device. And at the end, what I get out of it is 2,048 ports of 100 gig that I can use for any top of the rack switches. It's a 204.8T non-blocking fabric. We had a good non-blocking and the leaf spine talk from Russ White before that. It's one of those fabric design. And we are running it pretty lean. Like we looked at the features, it's underlay only, IP v4, v6 fabric. By doing this, what I get is about 40% reduction in cost. And that's after we have standardized on single mode 500 meter DR4 optics versus what we were doing before. Hey, this is SR, this is long reach. Cutting down all of that, just have one optics overall. And we also gain in terms of latency. Going from deep buffer to shallow buffer here, it's a significant improvement in latency. Now, the monitoring part, the data collection, so we are leveraging all these different sources, telemetry, gRPC, syslog, SNMP, CLI, and Everflow is something that we are working on now. More details into the data sources, what they are doing. So for control plane and network topology, we are looking at SNMP. For system events, it's syslog. and various counters, port counters, and the buffer counters. It's using streaming telemetry. Again, Everflow is there in works for packet telemetry. And the tools we are using, we are building in-house and partnering with, partnering with outside vendors also to collect the data and make some sense out of it. Unlike the traditional tools where they are used just for the monitoring purposes, hey, up, down, we want to do something more in this core. Few things we are looking at are using the machine learning capabilities for pattern recognition and drifts. So a few things that we have as requirement are, I'm not going to configure any threshold on any of the counters. They have to be adaptive and more of like machine learning kind of. You see the pattern, let it run for a week or more, and when there is a drift for more than a certain amount, it causes an alert. Other thing we want to get out of it is to detect the gray failures, which is more important for SONiC the way it behaves. If the box is up and running and interfaces are up, but suddenly I drop traffic, we need to detect that. And that's not based on any traditional alert like, oh, something went down. In this case, nothing went down, but we are learning it from the patterns and from the drift. The third one, we need to look at some of the correlation pieces. So when something goes wrong, I get 30 events. And I want this tool to be able to correlate them. Hey, they are all the events related to one incident, so alert me only once. I mean, there's detail available, but I need only, they are one, so I need only one incident to be troubleshot. We did, so this is one of the features which is particularly interesting to me, because we were looking at traditional vendors to build us something, hey, why it takes so long to reboot? And we have been asking the feature velocity or whatever, never got it. And SONiC has it now. The fast reboot. I still get messages from the guy working in lab, hey, I loaded all the configs, and I rebooted the box. Box is going for reboot, and I'm going out for lunch. So with the fast reboot, we can reboot the box in less than, the requirements say 25 seconds. Conservatively, I put here 30 seconds. So we did some demos, and I have the screenshots here to share. So on the left, it shows fast reboot loading time, and on the right is a warm reboot. We are going to look at the fast reboot today. So the control plane, so the state of the forwarding DB and the ARP table is saved before the control plane goes down. And data plane is not cleared until the control plane has come back and it's ready to reinitialize the data plane. Here's the setup. On the top, we have two boxes running SONiC, and at the bottom, server 37 and 39 running iPerf. So the top two windows here are showing those two switches, the steady state, and window marked 1 showing iPerf turning on. Now, if you could read on the window 1, I issue fast reboot command, and the iPerf doesn't show any disruption. There's no disruption in data plane yet. Once the control plane is up, the data plane gets reinitialized, and that's when I saw only 15-second disruption. SONiC as open source, there's a lot to read and some reference that we use for building this slide deck. Thank you. Questions?
Rüdiger Volk, Deutsche Telekom. Looking at the slides, I seem to detect a gap in, well, okay, maybe a roadmap. I'm seeing mention of SNMP
Yes.
and gRPC, and for the access to data, I would have expected to see netconf or restconf somewhere in the picture. And for the data modeling, I think I didn't see anything. My humble observation is that the data modeling using Yang seems to be a fairly interesting development. And to me, it looks like if you don't have it in your roadmap and picture, you might actually miss a train that's leaving. Can you comment?
Yeah, so the open config is supported. The other models are there. The way I'm showing is like how we are deploying it at Comcast. There's a lot more than this. I am not so sure about some of the other data models. I mean, if anyone else want to comment.
Rahul Agarwal.
Hey, Rahul.
Rahul Agarwal, I'm with Octera. We've been working with Comcast on this. So just to add to what you just said, actually SONiC does support RESTconf. So it has a REST API. It's a pretty sophisticated REST API. And it does support open config-based models. And in fact, what's been deployed does have a network model which uses REST as well as open config. But of course, it comes over gRPC.
Yep, thank you, Rahul. And to mention, we are working with Rahul and his tool, Octera, to develop the internal tools. Okay, thank you.